In this video, we'll look at the properties of water. Water is a unique molecule because of its small size, its bent shape, highly polar covalent bonds, which we have discussed in an earlier video, and its overall polarity. The unique structure of water gives it some unique properties, largely due to its ability to form hydrogen bonds. These properties include water being cohesive, adhesive, denser as a solid than a liquid, and able to absorb large amounts of energy. These are the reasons why water forms the basis of all life. Let's take a closer look at the properties of water. When we say water is cohesive, what it means is that there is some amount of binding between like molecules that results in a surface tension that is high. Water is also adhesive, meaning that there is binding between unlike molecules, for example, water and the side of a test tube. This property is the reason why water droplets move along a surface as they do. If you look at a picture of a test tube that contains water in its liquid form, you can see that there are hydrogen bonds that form between different water molecules. There are adhesive forces between the water molecules and the surface of this test tube, as well as cohesive forces between two water molecules. As a result, there is high surface tension at the surface of water, which enables some organisms that have a lower weight to walk on the surface of water. Water is also a very efficient solvent because of the covalent bonds in water being polar. This is because oxygen has a greater electronegativity than hydrogen. As a result, oxygen develops a partial negative charge, while hydrogen develops a partial positive charge. This enables oxygen to form hydrogen bonds with other molecules that are electrically charged. Hydrogen bonds are weak electrical attractions between partially negative oxygen of one water molecule and the partially positive hydrogen of a different water molecule. Hydrogen bonds can also form between a water molecule and any other polar molecule. Because oxygen is more electronegative than hydrogen, oxygen pulls the electrons that are shared between the two atoms toward itself, resulting in a partial negative charge on the atom. Hydrogen, on the other hand, develops a partial positive charge. This enables hydrogen bonding between two water molecules and subsequently between multiple water molecules. Hydrogen bonds are continuously forming and breaking between water molecules in solution. Solutions in which water serves as a solvent are called aqueous solutions. The solutes, which are the substances dissolved in water, can be hydrophilic, as shown in the image here, where sodium chloride dissolves in water to form sodium ions and chloride ions that are electrically charged and thus interact with the partially negative oxygen atoms in water. Solutes can also be hydrophobic, as shown in the second image, where this hydrocarbon contains mainly nonpolar covalent bonds. These molecules, not being electrically charged, don't interact with water molecules around them, thus leading to a certain amount of repulsion between hydrophobic molecules and water molecules. Amphipathic molecules, on the other hand, have both polar regions, which are hydrophilic, as well as nonpolar regions, which are hydrophobic. So the polar regions can interact with water, and they're oriented toward the outside of structures called micelles that these molecules form when mixed in water. And the interior parts of the micelles contain mainly the hydrophobic regions of these amphipathic molecules. A common example of amphipathic molecules are those found in detergents. These molecules form micelles, trapping dirt on the inside. Pure water has the ability to ionize to a very small extent into its constituent hydrogen and hydroxide ions. The concentration of these ions is 10 to the power of -7 molar, and the concentrations of both the populations are equal to each other. Molecules called acids and bases change the hydrogen and hydroxide ion concentrations when added to water. Acids increase the hydrogen or proton concentration in solution, and bases reduce the hydrogen ion concentration in solution. The concentration of hydrogen ions in a solution is measured by a unit called the pH. The pH is equal to minus log to the base 10 of the total hydrogen ion concentrations within that solution. Changes in pH of a solution can affect the shapes and functions of molecules, rates of many chemical reactions, ability of two molecules to bind each other, and the ability of ions or molecules to dissolve in water. Let's look at the pHs of some of the commonly found solutions in our everyday life. Oven cleaner has a pH of between 13 and 14, meaning that it has a very low concentration of hydrogen ions, making it a basic solution. On the other hand, our stomach acid has a pH of less than 2, meaning that it has a very high concentration of protons, making it an acidic solution. Coming back to our formula for calculating the concentration of hydrogen ions, we can see that pH is inversely proportional to the hydrogen ion concentration within a solution. So, when the pH goes up, hydrogen ion concentration goes down. And when the pH goes down, hydrogen ion concentration goes up, meaning that the solution has a high hydrogen ion concentration. Let's look at a video that shows why maintaining pH is so important.
We're going to show you something with aluminium today. And the thing is, we've got here Coke cans and Pepsi cans as well, so that it's fair. But when Neil gave them to me, I had a look inside, and you can see there, this one has quite clearly rusted. So these Coke cans are made of aluminium, whereas the Pepsi ones are steel. That's why we can only use the Coke cans to do this next experiment. So what we're going to do with these is to show a property of aluminium and how it reacts with both acid and with base. And that means it's a substance that's amphoteric. What we're going to do is we've got a solution of sodium hydroxide, that's our base, and we've got also hydrochloric acid, and then Neil's going to put the acid in and I'll put the base in at the same time, and we're going to see what happens to the aluminium cans. Here we go. Oh yeah, straight away you can see the bubbling there with the base. Clearly you've got a very vigorous reaction in both cases. So what's being generated here is sodium aluminate. What's being generated over there in the acid can, oh my word, is aluminium chloride and water. We expected reaction with both, yeah, I hadn't anticipated to be quite so vigorous. I hadn't expected it to be quite so, wow! That is brilliant. So this is obviously a very vigorous, hot reaction. You've got a lot of fumes being given off, which is a good job why we did it in the fume cupboard. You can see all that smoke being drawn up into the extraction fan. I honestly thought the acid would have done more damage. Because when you think of acid, you always associate acids as being the evil guy of the chemical world. I think those Pepsi cans have gotten off very lightly. They may have had their tops cut off, but they've met a fate far better than the Coke cans here. Good old Pepsi for making them steel. What's left is just the plastic around the outside of the can. All the metal's been converted to sodium aluminate, and that one's still going. The acid is still eating away at that can, and again it's just leaving behind the plastic coating.
So that's why pH in our bodies needs to be highly regulated unless we want to meet a similar fate like those Coke cans in the video. So how do we maintain a stable pH within our body? Here's where buffers come into the picture. Buffers are solutions that help maintain a stable pH. Now, we can tolerate small pH changes in our body, but any more than that can lead to disastrous effects. Buffers help to maintain a constant pH. Our blood has a pH range between 7.35 to 7.45. To help maintain this pH, an acid buffer system exists in our body which can generate or release hydrogen ions to adjust for changes in pH. One example of this system is the carbonic acid buffering system. This concludes our discussion about the properties of water. On this slide are listed the questions that I would like you to be able to answer. Thank you.